Hello and welcome to this video about electric force. We're going to look at Coulombs Law, field forces, finding the resultant force on a charge, and electrostatic equilibrium. You probably intuitively know this, but the closer two charges are to each other, the greater the force is between them. This could be either an attractive force or a repulsive force. But if we were to move these two charges closer together, so we had a smaller radius, there would be a much greater force between them. How much greater would that force be when we change that distance? Well, we can look at Coulombs Law. It's this equation, and that gives us the mathematical relationship between the force and the distance between the two charges. Coulombs Law is represented here. F is for the electric force. This small k sub capital C is a constant, and this constant is Coulomb's constant. Coulomb's constant has a value that differs depending on the units that you use. The SI units are Newton meter squared per Coulomb squared, and the actual value is 8.9875 times 10 to the ninth. We're going to just shorten that to 8.99 times 10 to the ninth for our calculating purposes. And then the rest of this equation here, this is a Q, Q1 and Q2. That would be the charge of one object and the charge of the other. And this is the distance between those two charges squared. Remember, force is a vector quantity, so we need to treat that accordingly. The electric force between two objects always acts along the line between the objects. And also, Coulomb's law is basically applicable only to point charges or particles and to spherical distributions of charge. Let's do an example together. Let's look at the electron and a proton in a hydrogen atom. They're separated on average by 5.3 times 10 to the negative 11th meters. We need to find the magnitudes of the electric force and the gravitational force that each particle exerts on the other. So let's look at the electric force first. I'm writing down things I know. I know the radius. When I go and I look on a chart or a table or back in my book or back at my notes, I know that the charge of an electron is negative 1.6 times 10 to the negative 19th coulombs. The charge of a proton is a positive of that value, and I know my Coulomb constant. I can find the electric force by this equation. I can simply plug values into that equation and solve. And we get our electric force at 8.2 times 10 to the negative 8 newtons, and those are the units. Now, to look at the force of gravity, I'm going to need to look on some tables and look up my mass of an electron, my mass of a proton, and the gravitational constant here, and then I'm going to use a different equation, and I'm going to plug values into that equation now and solve for my force of gravity. And when I do that, I get my force of gravity being equal to 3.6 times 10 to the negative 47 newtons. Wow, that is tiny. Very, very little force of gravity there, which actually makes sense. The force of gravity is a much weaker force than the electric force. So we've just seen that the electric force is a much stronger force than the gravitational force. What's similar about these two forces? Well, both the electric force and gravitational force are field forces. We learned about those before. A field force is a force that is exerted by one object on another, even though there is no physical contact between the two objects. So the electric force and gravitational force are similar in that they're both field forces. They're different in that the electric force is much stronger than the gravitational force. Another difference between electric force and gravitational force is that gravitational force is always attractive. Electric force has both, it can be attractive or repulsive. One other way you can realize or recognize in real life that the electric force is indeed stronger than gravitational force is that think about the amount of charge required to overcome the gravitational force between particles. Like if you rub a balloon against your hair and hold it directly above your hair is going to stand on end because it's attracted toward the balloon. contrary to the gravitational force that is acting on it. So that's just another way to recognize the strength of the electric force. Now remember, because force is a vector, if we have many different charges acting, interacting and acting on another charge, we're going to be needing to look at the resultant force on a charge. And we do that just like we did before when we found the resultant quantity of a vector, and we found the vector sum of all the individual parts, all the different forces that are acting on that charge. We're going to have to take them apart, look at all those different vectors, add them up, and that will give us the resultant force on the charge. That's a principle of superposition, and probably the easiest way to do that is to just do an example together. Let's say we have 3 point charges at the corners of a triangle. We have charge 1 with this much charge, charge 2 at this much charge, charge 3 with this much, and we need to find the magnitude and the direction of the resultant force on that third charge. I'm not going to rewrite these charges just to save some space, but I'm going to underline them just because they are written right here. There's charge 1, charge 2, and charge 3. If I consider where my charge 3 is, I'm going to draw a force diagram illustrating the forces that are acting on it. Charge 1 is right here, and it is exerting a force that direction. And the reason it's that direction is that notice that charge 1 and charge 3 are both positive, so it is a repulsive force that is pushing, in essence, this charge away. There is another force between charge 3 and charge 2. Here's charge 3 and charge 2, so this is my charge 3. The force between charge 3 and charge 2 is an attractive force because charge 2 is negative, charge 3 is positive. So there's going to be an attraction going this way. The force will be in this direction between charge 3 and 2. The resultant force would be indicated here by this dashed line. That's going to be my total force on charge 3. Now that I have drawn my force diagram, I can calculate these individual forces using Coulombs Law. I'm going to calculate the force between charge 3 and 1 first, between these two charges. I'm going to plug in my Coulomb constant, the charges for each of those, charge 3 and charge 1, divided by the distance between them. You can see the distance between them is 5 squared, and I come up with 1.08 times 10 to the negative 8th newtons. That represents this force. And I'm going to calculate this force. And when I plug all of those values in, here's my Coulomb constant, the charges of charge 3 and charge 2, and the distance between them is 4.00 meters squared. I come up with 5.62 times 10 to the negative 9th. Notice I didn't include the negative sign. I'm not including the positive and negative signs because they're not really of consequence to me. I know what direction my vectors are going to be from my vector diagram, and so I'm using my vector diagram to keep track of whether the what direction those forces are going. Okay, so I redrew these for us so we have a little more room. At this point, I'm going to need to consider the direction of each of the vectors because I'm going to add the x and y components together. I'm going to look at the force between charges 3 and 1 first, right here. I'm going to separate it into its x and y components, and I'm going to look. We know from this diagram that this angle theta is 37 degrees, so this angle theta also is going to be 37 degrees. And I can calculate f of y and f of x, the x and y components, for that force between charge 3 and 1. So I know this angle, so I can take the cosine of this angle. That gives me f of x divided by cosine of this angle equals f of x divided by this hypotenuse, which is the force between the charges 3 and 1. I can put in cosine of 37 degrees for that theta and solve for f of x. Now I can find f of y, and sine of theta equals f of y over the force between 3 and 1. I can rearrange that equation and solve for f of y. And I get f of y equals 6.50 times 10 to the negative 9th newtons. These are the x and y components for this force vector. Now let's look at the second force vector between charges 3 and 2. That would be this one. So for this force vector, you can see that there's only an x component. So the entire component is the x component. So it is, here, right here. For force between charges 3 and 2, I have 5.62 times 10 to the negative 9 newtons, and I'm going to put a negative sign because it's going in the negative x direction. F of y equals 0 newtons because there is no y component to this force vector. Now I'm ready to add these together to get my total force on charge 3. I am going to add for my f of x total this f of x and this f of x, which is actually 8.63 times 10 to the negative 9th minus 5.62 times 10 to the negative 9th. My f of y total is going to be f of y plus f of y for each of those force vectors. So my f of y total is simply 6.50 times 10 to the negative 9th newtons. So now I'm going to redraw these two components of my resultant force vector. This will be my resultant force vector, and I'm going to use the Pythagorean theorem to find the magnitude of this resultant force. And it's just a squared plus b squared equals c squared. I'll spare you the details on that, but obviously my a squared plus b squared is this squared plus this squared equals my f sub r squared. Take the square root of both sides, and this is my answer for the magnitude of that force. And just to clarify where these numbers came from, they're the total force, so I just added the total. They came from here. I can find the angle here now. The tangent of theta is just fy total divided by fx total. And theta equals 65.2 degrees. You could say north of east or up from the positive x direction, any way you'd like to specify that. So now we're going to talk about equilibrium. Remember, Newton's first law told us that the net external force acting on a body in equilibrium must equal 0. Well, in electrostatic situations, the equilibrium position of a charge is the location at which the net electric force on the charge is 0. And this is a nice idea. Let's put this idea to work in an example. We have 3 charges lying along the x-axis. A positive charge at 15 microcoulombs, and this is its position. Another positive charge, 6.0 microcoulombs at the origin. At what point on the x-axis must a negative charge, we'll call that Q3, be placed so that the resultant force on it is 0? I just drew some of this information in a diagram for us, and we are going to want to place our charge Q somewhere in the middle, Q3. If we think of the distance between these two charges as some distance p, then this distance here between these two charges is going to be 2.0 minus p. Now we know that at equilibrium, the force here is going to be equal to the force here. Here, if I add a little kind of a force diagram here, I know that this has a negative charge. Each of these are positively charged. There's an attractive force on charge 3 in this direction and an attractive force in this direction. At equilibrium, these two forces would be equal. I can call this force the force between 1 and 3, and I can call this force the force between 2 and 3. So I will write that down. At equilibrium, those forces will be equal. I can substitute in my Coulombs Law equation now, because I know my electrostatic force, or electrical force, is going to be equal to this equation, and I went ahead and substituted in the representations for that. So now I can cancel out like terms. This constant cancels out on both sides. So does charge 3. It doesn't really matter what the charge on 3 is. It cancels out on both sides. Now I can substitute values in for Q1 and Q2, and I can see that these also are like terms, so they will cancel out as well. If I cross multiply, I end up with this as my equation. And now if I take the square root of both sides and then isolate p, I can end up with an answer for p. Here I took the square root of both sides, and I know this is kind of messy and awful. I'm going to take this up here now. I'm going to divide both sides by the square root of 15. And I can actually punch in 6 divided by 15 and take the square root of that on my calculator and then distribute that throughout this term. And I can finish up the algebra here and solve for p. I get 0.80 meters from Q2. That is the location of this charge. Here's some ideas for advanced proficiency, and I look forward to seeing what you come up with, and we'll see you in class.